Hello, welcome to my project. My name is Sarah Al-Nouri and I will be talking about the following fluid concepts: drag force, pressure drop, and pressure distribution. This is all for project 6. We were given 3 questions that include these following concepts. Each topic I'm gonna discuss the motivation and concepts, the method and assumptions I used, the results and the calculation of this question, and the support conclusions. Question 1. Water flows over two flow plates as shown below. The free stream velocity is the same for both plates and the flow is laminar. The second plate is twice as long as the first plate, but both plates have the same width. The answer that I chose was the last one. Let's find out why. The effect of fluid flow on a solid may be of interest in some applications. This entails the concept of the drag force. So what's the drag force? It's the force in the direction of the flow exerted by the fluid on the solid. In this case, it's the force exerted by water on the flat plate. When the wall of the object is parallel to the direction of the flow, the drag force is due to the wall shear. So some numerical values were assumed in order to carry out a numerical method. Example to this question: velocity of 1 meter per second, the kinematic and viscosity and density of water were used, and the length of 4 and the width of 10 were taken for these plates. The length is the length of the first plate. So the assumptions outside of the given were that there were no outer environment or edge disturbances, and the shear stress decreases along the plate. So a momentum balance will be applied on the system. Then the equation will be specified to Cartesian coordinates. The equation will be simplified to make the drag force appear in it. The assumed values are then substituted into the equations. Then we will obtain a relationship between the two drag forces in order to know the answer and the relationship between them. Using the momentum balance or the Navier-Stokes equation in particular from the appendix, we cancel the terms that are irrelevant to the given. The flow is only happening in the x direction and the gravity is in the y direction, so it cancels from the equation. So introducing the drag force into the momentum balance equation will give us this form of the equation. The change in velocity with time and the external force are constant, so we're going to focus on the drag force for now, which appears as the last term in the momentum balance. And one term that appears, and as shown in the formula to the right, is AP. AP is the cross-sectional area of the particle, or the plate in this case, which is a rectangle. So for the first plate, it's just the length times width, whereas for the second one, it's 2 times the length times the width. Then the drag force is found according to this. It's expressed with these given parameters, and so we find out that the drag force coefficient CD is dependent on the length. So that means that plates 1 and 2 do not only have a different drag force, but a different drag force coefficient. That's why they differ, in addition to the length. So after finding out that this is the equation shown in green for the drag force coefficient, we find that it's a function of the Reynolds number, and we can express the CD in terms of these parameters. So taking the ratio of the drag forces will give us a value of 1.4 between the force 2 over force 1. After taking the ratio of the two forces, it was found that F2 is greater than F1 by 1.4 times, and even solving for the drag forces numerically using the assumed values before in Excel gave the same result. So, in conclusion, the drag force F2 is greater than F1 by 1.4 times, so it's the last choice. The bigger the length of the plate, the greater the drag force. So that means for flat plates with laminar flow, length is proportional to the drag force. Question 2 is the following. A two-dimensional gate is submerged in water, as seen in this figure below. Choose the figure that best represents the pressure distribution of the water on the left-hand water side of the gate. Surprising thing about fluid problems is that some of them do not encompass forced motion. This problem involves the pressure distribution in a static water, so this in turn has an effect on the submerged gate. This concept can help in predictions of static atmosphere distributions. The assumptions and the method that is going to be used is the fluid velocity is taken as 0, so the system is in either static condition. The pressure change happens because of the weight of the water, and the pressure is normally a perpendicular force. Pascal's law will be applied on the system. The law is only applicable to fluids at rest, so the water is assumed at rest, no movement, and its density is incompressible. Because water is incompressible, that means that the density variation with the depth is negligible. A famous equation known to include the pressure is Pascal's law. Pascal's law says that the pressure is equal to the force over the area. It also has two concepts. One is that the pressure acts uniformly in all directions on a point or volume of a fluid. And in a fluid confined by solid boundaries, pressure is perpendicular to the boundary, so the force is normal to the surface of the boundary. Applying a force balance will incorporate the pressure into the equation, considering that it's a rectangular fluid element with height delta z and length delta x. The gravitational weight is the last term before the 0. So dividing by delta x will yield to the change in pressure equation. The above equation suggests that the pressure is proportional to depth. Pressure in water increases with depth because more water lies in deeper layers. The effect of extra weight on the deeper level is balanced by an increase in pressure. The hydrostatic pressure always acts perpendicular to the plane of the body. So we will see later that it ends up being directly proportional to the distance of the point from the free surface of the water. This can also be seen by this equation that we derived. From the 5 choices of the figures given, these two pressure distributions highlighted in blue are eliminated because the pressure is not normal to the gate surface. As you can see, the distribution is not perpendicular. As for the yellow square graph, the pressure distribution is also wrong because the pressure at the edge is shown to be 0 at the top edge, and this is not correct because the gate is fully submerged in water at a certain depth. The one next to it in purple is also wrong because the pressure varies with depth, and this shows a constant distribution. The last one is the correct one, the one in red, because it varies accordingly with the depth and it is normal to the surface of the gate. So, in conclusion, pressure in water increases linearly with the depth. The reason is proven by the fact that the pressure is proportional to the depth. It acts normal to the surface, and the pressure of the fluid at rest increases with the depth because of the added weight. In a fully submerged system, pressure has a value and it gets larger with deeper layers. The third and the last question is the following. Water flows through two smooth pipes with the same diameter and length as shown below. The flow rate through the second pipe is twice than that through the first pipe. Both flows are laminar and fully developed. Circle the letter of the statement that's correct about the pressure drop, pressure difference over the pipe length. I chose the last one because of the following proof. Let's see how to do this. Pressure drop is an important concept to master in chemical engineering because it affects many tubular equipment like reactors, for example. It's crucial to understand this concept in order to know how to design a reactor and minimize the pressure drop that influences its effectiveness. So we assumed numerical values for the question 3, diameter of 2, a length of 4 of the pipe, and pipe 1 has a mass flow rate of 1 kg per second, and I took the density and viscosity of water as the following, as you can see. So the method and the assumptions I have taken is that since the flow is laminar and fully developed, like given in the question, the Hagen-Poiseuille equation derived from the Navier-Stokes equation is the one that's going to be used to find the pressure drop. So the following assumptions are considered in order to continue with this derivation. We have a cylindrical pipe of constant cross-section. The flow is laminar and fully developed. The fluid is Newtonian with a constant density and viscosity. We have steady-state flow, and end effects of the pipe are ignored. Once again, the momentum balance or the Navier-Stokes equation is going to be used. Since the flow is only axial, that means we only have Vz as a function of r. V theta and Vr are both 0. Cylindrical coordinates were chosen and the momentum equation becomes the following. The convective acceleration term disappears because the continuity equation is satisfied. So integrating twice will yield to this last equation on the left. Boundary conditions shown in this purple box were no slip at the wall and that there is a finite velocity at the center. So we have two constants. G was found to be this much and C was found to be 0. This all leads to the Hagen-Poiseuille equation, which is shown here. So the mass flow rate can be derived from this equation as well. And in turn we can find the mass flow rate for pipe 1 and pipe 2. Since pipe 2 is 2 of the mass, the equations were also similar to each other, but the second one had a 4 in the denominator. So in Excel, the pressure drop value for both pipes was found, and the value for the pipe 1 was less than the value for pipe 2. The pressure drop in pipe 2 was shown to have a bigger value than the pressure drop in pipe 1. This can even be proved by plotting a graph in Excel against the pipe length, which was 4 meters as assumed. And as you can see, the delta P for the second pipe has a steeper graph, the one in orange. So in conclusion, the mass flow rate has a significant effect on pressure drop. The higher the mass flow rate, the higher the pressure drop. That means that mass flow rate is directly proportional to pressure drop for the case of laminar flow in smooth circular tubes. So the last choice is the correct choice according to this proven theory. Fluid mechanics and dynamics is an important concept that's fundamental to most engineers. Force and momentum balances are beneficial in deriving the famously known formulas, as we've seen, of the drag force, hydrostatic pressure, and the Hagen-Poiseuille equation. Excel was also a useful numerical tool that was able to validate what I wanted to show. Thank you so much for listening to my presentation.